Have you ever wondered how electricity travels hundreds of miles from a power plant all the way to your phone charger? It's a journey that involves some seriously high voltages, but the outlet in your wall only provides a tiny fraction of that power. So, how does this massive step down happen? The unsung hero of our electrical grid is a device called the transformer. It's everywhere, from those big gray cans on utility poles to the little black box on your laptop cord. Today, we're going to demystify this essential piece of technology and understand exactly how it works. It's magic. So what is a transformer, really? At its core, a transformer is a device that transfers electrical energy from one circuit to another through electromagnetic induction, usually with a change in voltage and current. It can step voltage up, making it higher, or step it down, making it lower. This ability is crucial for efficiently transmitting power over long distances. To understand why, we need to remember a basic electrical principle: power loss. When electricity flows through a wire, some energy is lost as heat. This loss is proportional to the square of the current. So, if you double the current, you quadruple the power loss. To minimize this loss, power companies do something clever. They transmit electricity at extremely high voltages, sometimes over 700,000 volts. By increasing the voltage, they can decrease the current while delivering the same amount of power. Because power equals voltage times current, less current means dramatically less energy wasted as heat in the power lines. This is where the first type of transformer comes in: the step-up transformer. At the power plant, these massive transformers boost the voltage way up for its long-distance journey. Then, as the electricity gets closer to our neighborhoods, a series of step-down transformers begin to lower the voltage to safer, more usable levels. The magic behind the transformer lies in a principle discovered by Michael Faraday in the 1830s: electromagnetic induction. Faraday found that a changing magnetic field can create an electric current in a nearby conductor. A transformer brilliantly exploits this phenomenon. The simplest transformer has three main parts: a primary coil, a secondary coil, and a soft iron core. The primary coil is connected to the incoming power source, and the secondary coil is connected to the load, the device that needs power. These two coils are not physically connected to each other. They are electrically isolated. They are, however, magnetically linked by the iron core. Here's the process step by step. When an alternating current, or AC, flows through the primary coil, it creates a constantly changing magnetic field around the wire. Remember, AC electricity is constantly switching direction, which is key. A direct current, or DC, which flows in only one direction, would create a steady magnetic field, and a transformer wouldn't work. This is a fundamental reason why our power grids use AC. The soft iron core is used because it's a great magnetic conductor. It concentrates this fluctuating magnetic field and channels it efficiently from the primary coil over to the secondary coil. Now, this rapidly changing magnetic field, guided by the iron core, cuts across the windings of the secondary coil. According to Faraday's law of induction, this changing magnetic field induces a voltage, and therefore a current, in the secondary coil. And just like that, we've transferred electrical energy from one coil to the other without them ever touching. It's like a wireless power transfer, but on a much larger and more efficient scale. The energy has jumped the gap via a magnetic field. So how does a transformer change the voltage? It all comes down to a simple ratio: the number of turns or loops in each coil. If you want to step the voltage down, you design the transformer so that the secondary coil has fewer turns than the primary coil. For example, If the primary coil has 1000 turns and the secondary coil has 100 turns, that's a 10-to-1 ratio. If you feed 120 volts into the primary, you'll get approximately 12 volts out of the secondary. This is called a step-down transformer, like the one in your phone charger that takes 120 or 240 volts from the wall and converts it to the 5 or 9 volts your phone needs. Conversely, if you want to step the voltage up, you simply do the opposite. The secondary coil must have more turns than the primary coil. If the primary has 100 turns and the secondary has 1000 turns, you have a 1-to-10 ratio. Feeding 12 volts into the primary would produce about 120 volts at the secondary. This is a step-up transformer, like those used at power plants to prepare electricity for long-distance transmission. The relationship is beautifully simple. The ratio of the voltages is equal to the ratio of the number of turns in the coils. Now, there's no free lunch in physics. The law of conservation of energy still applies. While a transformer can change voltage, it can't create power out of thin air. In an ideal, 100% efficient transformer, the power going into the primary coil is equal to the power coming out of the secondary coil. Since power is voltage times current, if you step the voltage down, the current must be stepped up by the same ratio to keep the power constant. So, in our step-down example, where voltage went from 120 to 12 volts, the current would increase by a factor of 10. If you step the voltage up, the current must go down. This inverse relationship is fundamental to how transformers balance the energy equation. Of course, no transformer is perfectly ideal. There are some minor energy losses. One source is heat generated in the copper windings themselves due to their electrical resistance. This is minimized by using thick wire. Another loss comes from something called eddy currents. The changing magnetic field in the iron core can induce small, swirling currents within the core itself. These currents do no useful work and just generate heat. To combat this, transformer cores are not made of solid iron. Instead, they are built from thin, laminated sheets of iron, each coated with an insulating varnish. These layers break up the paths for eddy currents, significantly reducing energy loss. You might also hear a faint humming or buzzing sound coming from large transformers. This is caused by a phenomenon called magnetostriction. The iron core physically expands and contracts slightly as the magnetic field fluctuates with the AC cycle, creating vibrations that we hear as a hum. This vibration also represents a small loss of energy as sound and heat. Despite these small inefficiencies, modern transformers are incredibly efficient, often achieving efficiencies of over 99%, making them one of the most efficient electrical devices ever invented. So, from the giant transformers at a hydroelectric dam to the tiny ones inside your electronic gadgets, the principle is the same. They use the elegant dance of electricity and magnetism to change voltage levels, making our modern electrical grid possible. Without transformers, we would face enormous power losses, and our world would be a very different and much dimmer place. They are the silent, steadfast workhorses that power our lives, quietly stepping voltage up and down, ensuring that the right amount of power gets to where it needs to go, safely and efficiently. Next time you see one of those gray cylinders on a utility pole, you'll know exactly what's happening inside. It is taking thousands of volts from the main line and stepping it down to the 240 or 120 volts that power your home. It's a brilliant piece of engineering based on a fundamental principle of physics, working 24/7 to keep our lights on. Thanks so much for watching. If you found this explanation helpful, please give this video a thumbs up and consider subscribing for more deep dives into the technology. that shapes our world. See you in the next one.